Yeah, okay. So, good. Right. Aziz, yeah. Yeah, yeah. Yeah. No, no, actually it's better. Like, I mean, I'll give just one talk. Okay, okay, great. Yeah, it's fine. So Walker, which, um, since you're giving the next talk, Vicary Heunen use the circle composition for the horizontal one, and for the vertical one they use a dot. Yeah.
I don't have a fixed convention.
Yeah, I mean.
And I don't like the semicolon.
No, I was thinking just use the tensor product, but that can be confused with.
No, I think the bullet is better.
Yeah, yeah.
I sometimes use a star.
Yeah, yeah. I'll make up notation as I go, I guess, because it's too.
Are you ready?
Yes, it's me.
Okay, so hello everyone. So today Redi is going to tell us about bicategories and monoidal bicategories. Okay.
Yeah, so I'm gonna do an informal, well, rather informal introduction to some ideas from two-category theory. Okay, so I believe these are the last two talks, and we are going to go into some of the higher categorical or two categorical ideas in categorical quantum theory. So today I want to talk just in general about two categories, etc. I'm not going to talk about Hilbert spaces and stuff like that. I guess some more interesting stuff will be presented by Walker next week, because he's more expert. He has expertise in some of the notions which come into play. And so, yeah. Now, I was going to give the last two talks, I think. So I asked Walker to do the next one. Because, yeah, for... It's, yeah. Yeah, so that's why I'm saying it verbally, so that people know next week it's going to be... Sure. Yeah. Yeah, okay. Okay, so let me start by just spelling out a definition of what is a two category, and then we will comment on it. Okay, so definition. The two category consists of the following data. Number one, so let's say a two category C. Number one, class of objects or a collection of objects, let's say. So let's say, I don't know, A, B, etc. And for any two objects A, B, we will postulate a category. Which I'm going to call CAB. Okay, so let's stop here for a second. Now, we already have some structure, so the pieces of data will go on, but let's comment on it first. When we define what is a category, we say that we have a collection of objects, and for every AB, right, this is a set, we say. So we say this is a set in the definition of category, normal category. In a two category, we ask for this to be a category, right? So this already has certain combinatorial implications. So let me just comment on those. So let's do a little commentary here. So now this category, CAB, will have objects and it will have morphisms. Now, the objects of this category CAB, we will think of them as arrows. So let's say objects F, G, etc., which we depict as arrows. So we have, like, say, F from A to B. Okay? And now the morphisms between these objects, right? So say we will denote them as alpha, beta, etc. with Greek letters, say. Now these are morphisms between or let's say, let's not overuse the morphism. So these are like arrows between arrows. So the objects of this category are arrows. And so the arrows between arrows, we typically denote them as this. So say you have F and G, and we do like a double arrow alpha from F to G. So this signifies alpha is a morphism from F to G in the category C AB. So this is how we think about them. So we have objects, and these regular arrows, which are the objects in CAB, we think of these as, so F and G here, we call these one morphisms. And the arrows between arrows, so geometrically we think of it as some sort of disk which fills this area between the two arrows. Okay, that's how you sort of visualize this. We call this a two morphism. Okay, so just saying that we have a category like this already gives us sort of a picture. Okay, and now these two morphisms compose inside the category CAB. So on top of that, we have composition in CAB. And what's that? It's just, so say we have a composable pair of two morphisms. So here we have like F and G and H. And what's a composable pair is something like this. So we have alpha from F to G and beta from G to H. So this compose into giving us something from F to H, which following Vicary Heunen is denoted beta dot alpha. So this dot here, so this is the composition operation inside the category CAB. This is also called vertical composition. So because you put two morphisms on top of each other in the vertical position and you compose them. Okay, so this also is called vertical composition. So we have three new terms. We have one morphisms, two morphisms, and their vertical composition. All of them encoded by saying that we have this category CAB. Right. So next piece of data is a composition functor which goes from CBC, I should say, yeah, I phrased this poorly, sorry. So I should say for all triples of objects ABC, we have a composition functor from CBC times CAB to CAC. And now let's point out, like I did there. So for ordinary categories, we ask this to be a function of sets. But in a two category, we ask this, I mean, since the three of these are categories, right, postulated like there, we ask of this to be a functor. Now, what are the implications? I mean, how do we interpret the data for this functor? Well, so first of all, right, if I take a pair of objects, so let's say I take, let's put it like that. Use the other color. So if I take a pair G, F, so this is now G is an object here, F is an object here, which means they are one morphisms. So I have this situation. I have G, I have F, composable one morphisms, let's say, in the ordinary sense. So this composition functor will give me an object in CAC, which we call G composed with F. So so this is like a normal composition of one morphisms. So this gives me A to C, G composed with F, or if you wish, we form the composite here. Yeah. Okay. Okay, but this being a functor means that it doesn't, so this is just what it does on objects, right? So what it does on morphisms is the following. So say I have, so let's put it like this. So say I have this pair, alpha from F to F prime in, sorry, let's put G's here to be consistent. So from G to G prime in the first category, and beta from F to F prime in this category. So this will give me like beta composed with alpha, which will be from G composed with F to G prime composed with F prime. And how do we draw this as a picture? So what does it mean to have this pair? So again, I'm going to have A, B, and C. This means that I have two morphisms in this position.
Isn't it the alpha and beta?
I think I wanted this to be beta and this to be alpha. Doesn't matter, but yeah. Yeah, sorry about that. So the picture will make things more good. So I have F and F prime, and I have my alpha from F to F prime, and I have my G, I have my G prime, and I have my beta from G to G prime. Now this will compose, this operation will compose these. So I apply that functor to this pair of morphisms, and what I get is a composite which we call beta composed with alpha. And the source and target of this two morphism are the one morphisms G composed with F and G prime composed with F prime. So this is what the action of this functor on two morphisms does. And the term we use for this is horizontal composition. So why horizontal is because we place two morphisms next to each other in the horizontal direction and we obtain a composite. Right. So I should go on with the definition, which means I should erase the first part of the definition. Yeah, this is what unpacking these definitions is a bit long. I hope the ideas are sort of clear. So let's recapitulate. We have objects, we have one morphisms, we have two morphisms. We can compose these in the vertical direction, and we can compose these in the horizontal direction. That's what I've said so far. Okay. Okay. So I'm sorry, I have to. I wish we had those, 9-board sort of huge things they have in Germany. Oh, okay. I would put these up and keep writing. Okay, so an important thing to point out, I'm still not done unpacking this piece of data. So what I've depicted so far is just the action of composition or morphisms in these categories. But now saying that this is a functor means that this composition should be preserved. Like I have two composable things, and like compositions go to compositions basically, okay? So let's put it like this. Plus composition should be preserved by this because it's a functor. And so what this means is the following. So we can draw a picture of what this means. It means, so i.e., if I have this type of configuration, so say I have f prime, f double prime, g prime, g double prime. So let's say here I have alpha prime, beta prime. So this is now a composable pair of morphisms in CAB. And so the whole thing becomes a composable pair in the product. And this should be a functor. It means that it preserves composition. What this really, how we think about it is that, okay, I have given you this configuration of cells. Okay, let's think about it very simplistically. Now, there are two ways I can go about obtaining the composition, right? First, I do the composites vertically and then horizontally. Or first, I compose these horizontally and then do the vertical composition. Okay, so this being a functor means that these two ways of composing give you the same result. So there is no ambiguity. So, given, so let's put it like this, given the following configuration of two cells, the two ways to obtain a composite agree. And we call this interchange law. And equationally, we write this. Okay, so what are the two ways of composing? First, I do alpha prime dot alpha. So let's do alpha prime dot alpha. So I do this composition, and I do beta prime with beta, and then I use my horizontal composition on the two composites. This should be the same as, well, I can do the horizontal composition of beta and alpha. So let's do, so I have beta composed with alpha, and I also have beta prime composed with alpha prime. But then these gives me vertically composable things. I can do this, so these two are equal. There you go. This is called interchange law, and basically saying that this composition is a functor amounts to these things. I haven't said anything about identities, but yeah. So let me say something about identities. So for all, we have identities, meaning for all objects A one morphism identity A, which is an object in the category CAA, and for all one morphisms I guess when I said this is a category, sorry. Yeah, it's enough to say this, right? Yeah, I don't need, okay. So this is a, okay, let's, yeah, okay. Let's not say anything here. And then, okay. Right, maybe I should just say a remark somewhere. So CAB is a category. This means, this entails that if I have an object which is like a one morphism, I always have an identity morphism, which we write it F. Just by saying that this is a category, I have identities for every object, which means there are identity two morphisms that look like this. But this saying the one morphism identity A from A to A, we cannot, like, it has to be postulated as a separate piece of data. Okay. And okay, good. So, okay, so this is the data. And now I have to state what kind of laws these satisfy. So, there is more actually. Okay, let me just quickly finish the definition because this part is not important. So, plus, let's say like this, additional data, which is associators and uniters. So I will do this sort of, yeah. Okay, so this bit, so let's call this star. So given 3 composable one morphisms, so let's say F, G, and H. Now, in a normal category, we have that, so maybe let's point this out as a remark. So we have that H composed with G composed with F is the same as H composed with G composed with F. So this is what we have in a category. We actually say this, right? We say composition is associative. When we go one step up in the structure, we postulate like isomorphisms here. So just like the associators in monoidal categories, right? They were like these isomorphisms. And similarly, so given this setup, we have an isomorphism so this is like, let me denote it as the associator, of course depends on FGH. And now instead of saying these are equal, I will say that I have an isomorphism between them. Okay, so this is from I think the associator goes the other way. Any preference, Walker?
So,
Yeah.
formally it should go
Left to right. Yeah.
left to right.
So this is good. Okay.
So, yes.
Yeah. Okay. Good.
I mean, it doesn't really matter.
I know
You're
it.
not doing laps
I know it doesn't matter, but just I forgot what Vicary and Heunen say. So from here to here, and this is an isomorphism in the category C AD. Right. And okay. Wasn't supposed to take that long, but I guess it has to be done. Right. So let's put a double star here. So we have uniters, and what these are. I guess if you sort of do some analogy with monoidal categories, you can kind of guess. But let's draw a picture. So let's say I put identity B here, and I have F, and I have F. Okay. So in a category, we say that identity B composed with F is actually equal to F. Right? Now, in a 2 category, we don't want these strict sort of stuff, but rather we say something like this. So there is an isomorphism between this composite and this. So we say an isomorphism in C AB, which goes from identity B composed with F to F. So it will be a two-morphism. We think about it like this. Okay. And the other way around. So what's the other way around? We do identity A. They have an F here. So again, in the normal category, this composite is equal to F. But now we will say that they are isomorphic, not that they are equal. So F composed with it A to F, and this is isomorphism in CAB. Yeah. So let's move this to isomorphism, say, in CAB, this and that. Okay, so this is all the data for bicategory. I mean, it is what it is, first of all. Nothing I can do about it. And second of all, you should really think in terms of like one morphisms and two morphisms, things up to isomorphism, things like that. So hopefully I will try to convey some intuition on how this stuff can be worked with, etc. in this talk. It's hard to do in one talk. Normally this would take 2-3 talks to get used to the subject, but so the definition is not over actually, but this is all I'm going to write. So there is like coherence for associators and uniters. So these are similar to those of monoidal categories, so I'm not going to write them down. Even if they weren't similar to those for monoidal category, I still wouldn't write them down. But I think we wrote them down once, so I'm not going to do it again. And we won't really go into using these rigorously, etc. Okay, we just want to have an idea of what's happening. Okay.
It is worth pointing out at this point that the definition that has been given here, while we're calling it a two-category, is most commonly in the literature called a bicategory.
Yes.
Precisely.
So yeah, good. Okay, so that should be pointed out. So remark the above is also called bicategory or weak two category. Yeah. So weak because, I mean, these things hold up to isomorphism and not strictly. That's the idea of weak. Okay, so someone said once that to do things with two categories, you just do what you do in categories and you put two morphisms, which is something I like. I mean, for instance, right, we have this sort of triangle. It's supposed to commute, but we have some space here for two morphism. So we just put this isomorphism here and here. And so we will see this come up this again. Okay, so this is what a bicategory is. Now, I think for pedagogical purposes and not to be sort of overwhelmed, I like to think about it in terms of structural complexity, both combinatorially and otherwise, and to make sense of some of the statements we want to make. Let's see how much time I have. Okay, 38 minutes to go through the definition. No, but there was also unpacking and explanations and everything, so good. Okay, so I like to use a heuristic, which I like to call table of structural complexity. And so it goes like this. So we have level 0, level 1, level 2. So this is the first row is complexity level. I guess you can use some other term, but let's stick to that. So here, what we have is that, so at level 0, we have sets. And how do we think of a set? Well, it's a bunch of elements. Okay? So this is like zero-dimensional because it's like just points. Okay? I could also avoid drawing the bag, just a bunch of sets here. And so in level 1, we have categories. And so now we do have sort of points which are objects of the category, but possibly like morphisms. So this becomes like one-dimensional. Okay. So in the next stage, sort of complexity, we still have objects, you know, arrows, but possibly like also arrows between arrows which fill sort of space, or like two cells, if you think in terms of topology, for instance. This is informal, of course, but it helps, because I mean, I think only through this sort of lens one can understand the continuity of concepts when we go from one step to the other. So really, like a two-category is like the next thing in the ladder of structure when you think in combinatorial terms like this. It's really simple, so I like the picture, right? And this will bring us, for example, to our first example of a two-category. Okay, so I'm going to use this table. Unfortunately, I can't fully occupy a board with everything I want to do here, but let's say like this. So now the collection of all sets, so the collection of all zero-dimensional things, forms a category. So we have the category of sets, which we denote as set, say. So we've been using this for many purposes. And now the collection of all these categories forms a two-category. So there is a two-category cat. So let me just say what it is briefly. So this is our example. And I guess we will see more in the next lecture, one more at least, related to Hilbert spaces. So cat is the two category with, so categories as objects, and now one morphisms, or let's say functors, are now one morphisms, and natural transformations, I think we defined these in the first couple of lectures. You can go review what's a natural transformation, but these are two morphisms. Okay, I'm gonna skip my favorite example and just move on. But there is a two category like this point, and since, I mean, we are always saying this is natural, this is a natural isomorphism, etc., right? Now, it seems that this notion of naturality like appears with categories as a necessity, so to speak, right? It's actually the reason to encode this notion of naturality, people define what a category is in the first place. And now, I mean, through this structural complexity stuff, we see that, oh, it's because categories form a two category. And that's what they're supposed to form. Okay, so this is the sort of bigger picture of what's happening. Right. Okay, so the next sort of theorem, which is mentioned in Vicary Heunen, I will also explain through this table. I'll just keep doing the three columns without saying what they are. Right. So in dimension 0 here, we have the notion of a monoid. Okay. So a monoid is a set with a binary operation and whatever, other structure. Now, one way to see how this is related with dimension 1 is to recall that these can be thought of as categories with one object. And just to remind ourselves how this works, so if I have a monoid M, sort of form this category. So let's just draw it like this. So we have a unique object, and the elements of the monoid say X. So I have X, Y, and M. So we draw them as arrows. And the composition in this category is multiplication in the monoid, right? So we just form this one object category. So this is multiplication in M, right? So normally we just say, well, we have, I don't know, Y times X. In dimension 0, all we can write is strings of letters, etc. So here, what we do is we draw this type of picture. So we have this sort of equivalence between these two notions. And now what we have in dimension 1 is the analog of a monoid, which is a monoidal category. Right? So it's the categorified monoid, if you wish. So it's a category with a binary product and all those long properties, associators, and things like that. Okay. And this statement can also be implemented here. I mean, there is an equivalence between a monoidal I mean, a monoidal category can be regarded as a two-category with one object. Now, this is tricky to state as a theorem. What does it mean that a monoidal category is a two-category with one object? Not much. Normally, we want to say that the two-category of monoidal categories is two equivalent to the two-category of two categories with one object, but that will take like a couple of hours to unpack, right? But as a relaxed sort of statement, and as Vicary Heunen stated, let's put it like this. A monoidal category can be regarded as a two-category with one object, and let's call this theorem. Okay, and let's just see how you go from one to the other, really. So if I have V monoidal category, so let's be more precise. So V tensor I, then what you do is you form the two category, which I want to denote BV to relate to that example. So this BV, of course, has one object, star, and now the objects of V become the one morphisms of BV. So you sort of push the structure one up, right? So one morphisms in BV, we say are the objects of V. So what we are really doing is what? So we have, for instance, a object of V, and we sort of depict it as an arrow. I mean, there's only one object, so this doesn't matter. You can think of it as a loop if you want, but I prefer to like lay it out as an arrow. Makes things clearer. Okay, so let's go on in saying what this is. Now, I should tell you what are the two morphisms here. So at this point, you can guess, right? So we have this dummy object. Now, objects of V become one morphisms, and morphisms in V become two morphisms here. Okay, so two morphisms in BV are morphisms in V. And so what kind of picture we get? So let's say I have like FA to be in V. This becomes, so now the objects are the one morphisms, and the morphisms become two morphisms. Okay. Now, what do I need the monoidal structure for? Of course, because I need to compose these. Okay. So let's just say composition for, well, technically it's horizontal composition in BV is the tensor product in V. And what do I mean by that is that if I have this scenario, the objects AB, morphism F, and let's say objects CD, morphism G, how do I compose these? I use the tensor product, which means that I get C tensor A, D tensor B, and G tensor F. Okay? So this is, if you wish to think in terms of, I don't know, topology, you suspend the monoidal category to form this type of two category. Okay? So this is sort of a sketch of how this works. As I said, to make a precise statement, you need to develop lots of language and theory. And you can ask me a question if you want, but yeah. Okay, so, right. Okay, in the table so far we have one example. We have this theorem. Okay. And I'll keep going. So I'm going to list 2, 3 more, I mean, as many items as I have time following. So we have what, half an hour? Okay. How much two category can you do in half an hour? Okay, so I will briefly say something about graphical calculus. Okay, so Vicary Heunen developed this type of graphical calculus for two categories, not in quite rigorous fashion, but it works. So let's just sketch the idea. So okay, so for cats, so for normal categories, remember the whole point is like, if I have a morphism A to B, graphically it's advantageous to sort of denote it in string notation like this. Okay. Right. So the strings are the objects and the nodes are the morphisms. You sort of invert the role. Here the arrow is the morphism and the nodes are the objects. Okay, now what to do about, let's just go by sort of structural complexity with that idea in mind. So what to do when we have, so in a two category, I have these one morphisms, and the basic situation that I find myself in is that I have a two morphism. Okay. Now how would I depict this in string notation? Sort of following the geometric idea, what you do is that you invert the dimensions of things. Okay, so what's the higher dimensional piece here? Is the two morphism, right? Is the two cell. So we make this now a node, alpha. Okay, so the two-dimensional cell becomes a zero-dimensional thing, which is a node, right? Now the one-dimensional things sort of remain one-dimensional because 0, 1, 2, 1, 2, 0, okay? So 1 remains 1. So we depict them as sort of these strings. So alpha goes from F to G. And now how do we keep track of the objects? We need a two-dimensional information. So objects become, let's use colors maybe. So this part of the plane represents object A, and I think no, in reverse, sorry. So this is object B, and the other side of the plane becomes object A. So yeah, they have nice pictures in Vicary Heunen. They shade these areas, etc., to let you know. But basically now, the zero-dimensional things here, which are the nodes, become sort of two-dimensional regions of the plane. And this is basically the graphical sort of string theoretic way of depicting two morphisms. And of course, these directions can shift, but for some reason, we have this convention, left to right, bottom to top, in reading this. Okay. Right to left, yes, okay. My left and right is not. So I don't know, I heard a rumor. I don't know if it's true, maybe someone else. So I think Penrose came up with with these type of diagrams. I think so. I read it somewhere. And for some period of time, he was wearing glasses that sort of reversed things. So he was seeing up and down and down. And so he wore glasses like that for some time just to see what happens. And this happened. So, I don't know if it's a legend or a story, but sounds like true. I read this on a forum or somewhere, like on a blog post.
The wellspring of all reliable information, a web forum.
Yeah, so yeah. He was experimenting with these.
You saw it as an undergrad or no? Okay. That's what I remember.
Yeah, so undergrads, you have to do some weird stuff.
It's entirely plausible.
Yeah. Okay, so this is an item. So, and again, we have this jump in complexity, which is nice to note, because it makes the transition smoother. Right. So the next item I want to talk about. So again, using my table. Okay, so here we have sets. So, right. So we have like the 0, 1, 2. So we have sets, categories, and two categories. And now, okay, so in a set, okay, how can I compare two elements of a set? Right, so I have a set which is just some elements. How can I compare two elements of a set? Well, the only thing I can say about two elements of a set is whether they are equal or not, right? So that's all the information you record. So here we have sort of, let's put it like this, comparison, sort of, well, let's just say it like this. So we can say x equals y or x not equal to y. I mean, that's the only sensible things we can say about some x and y. Right. Now, jump to a category. Okay, so let's say I have whatever, some category C. So how can I compare two objects? Well, I can always say whether they are equal or not. But we have this extra notion of isomorphism, which is a notion of sameness, which is more relaxed than this. And it happens because we went up one dimension, we have more conceptual space, right? So we can say whether things are isomorphic or not whether they are equal or not. Okay, so we have a notion of comparison. We can say x isomorphic to y. We have this notion of isomorphism. Right, so things relax when you move one bit up. Now, how do we say what is an isomorphism? Well, we just say there is f from x to y and g from y to x such that if I compose these two are the same, so g composed with f is identity, and f composed with g is identity. So, okay, so we have here. And so when you go further in a 2 category, we still can say whether things are equal or not. Because I mean, we have some objects, we know if 2 objects are the same or not. We still can speak about isomorphisms. I mean, if there is f and g such that these things are equal, things are isomorphic, no problem. The more interesting notion, again, we have this item of comparison. We can relax some more and have something more meaningful called equivalence. Now, how do I understand what an equivalence should be, right? I mean, this could be an exercise, write this definition. The way you do this, and I sort of wanted to get this point across, is that you look at what's happening for categories, right? So here we ask that G composed with F is equal to identity X, right? So if I want to, in a 2 category, we have even more room. So I can say that I have an isomorphism between GF and identity X. Because I have morphisms between morphisms, which means I can compare morphisms by isomorphisms. And so I just change the definition and say that I have an isomorphism here. I get this notion of equivalence. So to write it down more precisely, well, you just say, take this picture and say GF is isomorphic to identity X in the category EXX, and FG is isomorphic to identity Y in CYY. And so we say then object X is equivalent to object Y. There are many ways to put this, but that's what it is. Well, this is how you push things, right, along dimensions. Okay, so there is a graphical way to put what an equivalence is. Should I do this? I don't want to do it. I don't think it's yeah, I will go back to the graphical stuff in a second. Okay, so we have this thing here. So for categories, this recovers the notion of an equivalence between categories. So I'm just going to say it in words because I'm too tired at this point. Right, but this is really what we want in a 2 category. Like in all the examples, it's this notion of equivalence that captures what we actually want to do. Right, okay, so next item on the table. Okay, so again, we have this notion of monoid, and we have this notion of monoidal category. And so we can make up a notion of monoidal 2 category. So if I asked you, what's a monoidal 2 category? Of course, the answer should be is a 3 category with one object. But we don't know what a 3 category is. It would take like a few hours to write down the whole definition. And we will not really go into writing, writing the full definition of what's a monoidal 2 category sort of is too much to do. I don't want to do it. But roughly speaking, very roughly speaking, this is a 2 category with multiplication. Right? So we have set with multiplication, category with multiplication, 2 category with multiplication. Just develop these things. Right. And now, how do I sketch what this is? One thing we want is that we want to multiply 2 cells. Okay, so it's just, say I have this, some alpha, and I should be able, so Vicary Heunen denote by box product, the product in a category, in a 2 category. So I want to sort of take this and multiply it with another cell. So let's give these names, F and F prime, G and G prime. Okay, so in a monoidal 2 category, what I'm able to do is I take two cells, I multiply them, and the result I get is, well, I multiply A and C, I multiply B and D, and then I multiply little f and little g here. So this is f box product G, f prime box product G prime. And then I multiply the 2 cells to get a cell. So beta box product alpha. So let's just say this, a monoidal 2 category is a 2 category where I can do this type of things. Okay, so I have a, again, we can say V, this is a 2 category, this is the box, the tensor product, whatever, and we have an identity object and possibly other stuff, but something of this form. Now graphically, yes, yeah, thanks. So to be consistent, yes, thanks. Okay, so there is a, so this type of graphical calculus sort of comes handy when interpreting monoidal structures. Right, because in here, how do we do the tensor product? Well, we just say we just write them, like stack them on top of each other, right? So we have like, if I have f a to b and g from c to d, when I write them like this, sort of diagrammatically signifies that I'm doing f tensor g in a monoidal category. So this has been like one of the themes of the whole seminar. And so could anyone tell me by analogy, how would we think graphically of that type of tensor product? So I'm going to multiply 2 cells. So each cell looks like this, right? So how do I graphically represent doing the multiplication? You stack two planes next to each other. Okay, so this thing here, in this thing, I do it. I mean, we just write it like this. So I have the alpha, which goes from F to F prime, and I'm not gonna shade the regions because it's sort of, well, whatever. So let's say we have this sort of plane here, and this part here is like B, and this part here is sort of A, and I have this plane, and let's hope this comes out nice. I have the beta, which goes from G to G prime, and I have this sort of plane which represents it. So this part, oops, this part of the plane is D, and this part of the plane is C. So if I put these planes next to each other like this, we read this as forming this. It's just placing them sort of next to each other. So it's a higher dimensional version doing this. So this is the type of stuff you get with these things. So see how much time I have. 15, good. So we are just in time to discuss duality a little. So I'm gonna, again, using this type of idea, I'm gonna discuss duality. So before I erase, do you have any questions or something? Define three categories, four categories, so you do it inductively. So it's not easy. Like, I mean, keeping track of all the coherence laws, writing them down is, I mean, it takes so much, it's so much data that it's impossible to keep track of it manually. So there are written definitions of 3 categories and 4 categories, but they are basically unworkable with. But by inductively, I mean, suppose you have the definition for n minus 1 category, maybe you can use this to define. No, I mean, there are proposals of that form using, say, Operads theory. So Tom Leinster has a book on the subject. But generally, it's not easy. So when you go with the infinity categorical version of these things, then you can write down precise definitions and yeah, exactly. So yeah. So if we just sort of assume infinity category theory and truncate down, that just gives us the notions. Otherwise,
so in some sense, climbing up this ladder is quite easy if you do everything strictly, which, for instance, is not what we're doing here, where you take like associativity and unitality, you strict, and you're just enriching the previous state in a strict sense. Yeah. But climbing each step with the correct coherence, where everything is weak simply, ends up being an absurd amount of data to keep track of. And so what Redi was alluding to with higher categories is basically that's a formalism to keep track of all of the data off to infinity, and then you can truncate. Whereas here, trying to write down even the definition of what's called a tri-category, which is a weak tri-category, or sorry, a category weakly enriched in bicategories is a nightmare.
So think, for instance, the complexity, if you think of it from the topological side of things, for instance, you form the fundamental groupoid. You can form the fundamental 2 groupoid, which is a 2 category. But we skip this example because this is quantum. Now, if you knew how to handle 4 categories perfectly, let's say, that means you should be able, for any topological space, to form the fundamental 4 groupoid. I mean, do we know anything about pi 4 of S27? No. So in some sense, writing these things down. Oh, okay, but good to know. So that means that we have a unique 27 morphism, or no, a unique, yeah, okay.
A unique 4 morphism in the 4 groups.
Yeah. Yes, but it somehow implies that we have perfect knowledge of fundamental groups, which we don't. So.
Okay, so to put this a different way, 4 groupoids or n groupoids should model homotopy n types. And so somehow, if you know everything,
yeah,
it should be equally easy to write down an arbitrary homotopy n type as it is to write down an arbitrary n groupoid.
Yeah, yeah.
And so it does get pretty complex.
Yeah, I mean, this is the whole problem, like with the, but until dimension 3, we can sort of do things like we're doing here, you know.
Okay, so I should compare it to the homotopy theory of 2 dimensions.
Yeah, something like, yeah. Yeah, I mean, you can sort of by hand write things down.
Yeah.
Some.
The pictures that he's drawing, you really can interpret these as 2-dimensional sets. I mean, there are multiple different ways to interpret a bicategory as 2-dimensional sets.
How do I think of this? Like the one.
So no, the picture, not the graphical calculus. The pictures that you draw there, you add a 0 cell for every object. You add a 1 cell for every morphism. You add a 2 cell for every 2 morphism, because the source of target is on the boundary of this. So like that thing that you've drawn there, A to B, F and G and alpha, that is topologically this. If you just take that 2 category, it has a disk with the cell decomposition, 2 0 cells,
2 0 cells corresponding
to 1 cell corresponding to A and B, 2 1 cells corresponding to F and G.
I dualize this to get the cell complex.
No, the diagram on the left.
I dualize the diagram on the right.
Yes.
Okay. So already the categorical picture, error picture is the cell complex.
Yeah.
So one way that you can see this is there's a nerve operation called Dustin-2 nerve that produces a simplicial set out of these things that really is.
You can do a geometric realization basically, and you yeah.
The simplicial set does. If you realize it, then you forget that things are not invertible.
Yeah, I don't care about the
yeah.
I just care about
yeah. Yeah, I mean, there are those things available. Okay, so let's do the last item maybe, so that Walker next time can assume all this stuff and just tell us something interesting. I mean, in the book, there are many interesting quantum notions done to categorically. Yeah.
I understand you're trying to be fair, but I looked at the chapter and there was maybe 2 examples that seemed one to me.
Yeah. Okay, 2 is enough. I mean, what? Yeah. I mean, 2 categories appear a lot. Like, if you stay in the game for long enough, it's unavoidable, some 2 category theory. So it's good to know anyway. So yeah, I want to very briefly see how, like, okay, in the stuff which I erased, sort of we had this, right? Take a categorical notion and sort of put 2 morphisms when appropriate, and you get the appropriate 2 categorical notion. Just replace equalities with isomorphisms. It's more complicated than that, but we can apply that idea to duality. So let's recall, I mean, maybe briefly in pictures. I'll explain this, I'll sketch it, okay? So what is duality in a monoidal category? Okay, so for monoidal categories, what do we say? So A is, I don't know, dual to B if I do have the structure map. So epsilon from I to A tensor B, which we depict. So we have this epsilon AB. So from I to A tensor B. And to make things easier, we just write this. And we have eta from B tensor A I, which we write as follows. So eta normally, according to our graphical calculus, is a picture like this. And to make things easier, we just say this.
The other way around.
I mean, in fairness, he didn't specify left or right dual.
Yeah. I mean, it's equivalent to whatever. So yeah. So we have these two, and such that the snake laws sort of follow. So I can start with this A B. So here is A, here is B, here is A again.
Actually, that one is right.
Walker is also right. We never studied two.
Yeah, I think there's a picture here.
I mean,
Epsilon is this one.
no.
The other one is
So this should
You
be.
can just say, you can change A dual to B to A right dual, right?
I mean, there's right dual, left dual.
Oh, I see.
Doesn't really matter. Yeah.
Okay, fine. Fair.
Yeah, I mean the
Let's not use the right.
the pictures will work. So here we have the B. So B, A, B, and so I have this. Well, in the end, I get an operation from B to B, and I say this has to be just identity. And so in monoidal categories, we had this type of stuff. Now, if I wanted to write these sort of diagrammatically, so what I do here, how many minutes? 4. Okay, good. So if I write a diagram out of, if I interpret this as a diagram, so what I do is this. So I start with A, and then there's also an invisible I here. So I go to unit tensor A, and then I go with the epsilon to A tensor B tensor A, and apply the associator to make this and then go to the last bit with the eta to make this A tensor I, and then just say this is isomorphic to A. And now the claim that those two things are equal amounts to say that going through all these is the same as doing this, which just means that this diagram commutes. Now, were we to be in a monoidal 2 category, what do? We say that there's an isomorphism here between this composite and identity of A. So So if this was a monoidal two category, what I would say is that, okay, I mean, I don't know, these become the boxes to be consistent or whatever, it doesn't matter. And we have an isomorphism from here to here, say. And similarly for the other one, I'm not going to draw, you get a similar sort of diagram. So this is the idea, like things that we wrote equationally, you put a two-morphism here, a two-isomorphism to be precise, and you relax the notion. That's how you get this type of duality. Now diagrammatically, it becomes trickier because these pictures only work right in dimension 1. So let me just very briefly, do I have a couple of more minutes? Yeah, okay. So just to see how this looks like. So the pictures look like this. So let me, okay, so I have, so how would we write epsilon I to a tensor B in this shape or form? So it will be something like this. So we have, so okay, A and B should be like pieces, two planes, right? And saying A tensor B means we stash them on top of each other. And the epsilon now should be like a, yeah, so let me just draw the picture. So we have something of this form. So it's like a fold. So there is a, like, maybe right like this, I'm not sure. So the unit here is like nothing, I, and then this bit of plane here is A, and the other side of the fold is B, and you sort of draw it like a fold. And similarly for the other one, you get a like fold like this way for the eta. And now the snake laws become something. I'll just draw one of them because it's fun. So now you get like a two-morphism which relates identity A to all this. Okay. Now all of this, remember, is this. So so basically you will do this. So you sort of apply one fold and then the other one. So this is the snake which sort of is in one side of things. And but on the bottom we just get identity. So this will be like, okay, am I that skilled? I doubt. So this will be sort of like, imagine taking a straight piece of paper, doing a snake on top, you get some sort of cusp here. And it's represented like this. So this will be from A tensor B tensor A with all the eyes and everything like that. No, this is the data. You just say we have this.
Are you supposed to draw a surface there?
Yeah, like you have a sort of snaky.
The cross section at any one slice of this is going to be equal to that?
Yeah, I mean the top part is this, so to speak.
And then how do you get to the line? As time progresses downwards.
Yeah, as time progresses downwards, I guess these, so this represents sort of just A. The right, so we have, so this plane is like A, and there is a fold in the middle which is B, and
something happens in the middle.
I mean,
Stretches out and it's,
yeah, I guess. I mean, there's so they call this cusp sort of. There's a thing here. This made perfect sense, but I'm too tired now. No, it really does make sense.
Oh, I see.
So in the book, do you see the? Yeah, this drawing is bad. I realize, but just wanted to point out how this is like a higher dimensional version of that, because you go like now you have to relate sort of the snake with this by a surface, you know, like it's that kind of idea, like you put this two-morphism, so you get these pictures, and
I was kind of like half joking, but is there sort of like homotopy thing going on there? Like from the top to the bottom?
not sure about that because Walker can answer.
So
Okay.
sort of like there are frameworks in which you can relate all of this to really very explicitly isotopy classes of surfaces, of labeled stratified surfaces embedded in R2 cross interval.
Yeah.
And yeah, so yes,
Yeah, kind of contingent on yeah.
You can also, okay, so this gets into also like the relation to topological theory, but you can also take like a cobordism, label it, decorate it with things like this, and then evaluate two categorical data on it, up to choosing some like Morse functions, which are sort of like turning this into a movie homotopy like movie. Yeah, that's cool. Yeah.
Okay, so now what? Any questions or are we done?
Yeah, I mean, they were discussing,
Oh, okay.
is there a
Sorry, yeah.
homotopy? So
There's more. Wait, no more.
no, I mean, material
Okay,
finishes here.
maybe then. Okay. Yeah, maybe there are questions, but
I don't know. Any questions before Redi goes? Okay, seems like no.
That sounds almost better. Any questions before we send him to the dark?
Yeah,
No, I think just the opposite. Redi is very elated right now. No